Let's get started. All right, so I hope everything's going okay. We're collecting this week's homework. Hope that worked out well for you. So we've just started talking about the Fourier transform, the Fourier domain, the idea of representing signals by their frequency domain representations. Hang on. Something odd is happening here. Okay. And we started off by looking at the problem, the question, the original kind of form of the Fourier transform, which was the Fourier series. If you have a periodic signal but a continuous time signal, you can represent it as a set of sinusoids, where the sinusoids are harmonics, have an integral number of cycles in the period of the periodic signal. And we can express that in terms of sines and cosines, but it's a little easier for us to express it a little more compact mathematically to use these complex exponentials, which for an integer k here, this is a combination of cosine plus j sine that completes k cycles in big T time, big T seconds. And so this is basically, by having complex values, we have both sine and cosine in one expression here, complex sinusoid and complex scaling constant here, and then by including both positive and negative k's, the positive complex sinusoid spins one way and the negative one spins the other way. So you can cancel out the imaginary parts to get real cosines and real sines as you wish, although this equation now works for periodic complex signals as well. So the assertion is that you can build some periodic signal by this way. There are various forms. It's like you can either approximate it. In general, you can only approximate it with a finite number of terms, although by letting m go as large as you want, you can get arbitrarily close to any periodic sequence. And then the question is, well, how do you find these coefficients? And what we tried to see last time was that we get the coefficients using this equation. This is like a recipe for how to build a signal from a Fourier domain representation. So sometimes it's called the Fourier synthesis form, and this is the analysis form. This is how to get the Fourier coefficients from a signal. And we sort of stated that it was this thing where you take the sinusoid you care about, you conjugate it, you then multiply that against the signal that you're trying to analyze, and just integrate that over one cycle of the periodicity, divide it by the length of the time you integrate it over, 1 over t, and that gives you the coefficient. And so this has a strong intuitive meaning to me. It's saying, yes, I'm building up this signal out of a set of sinusoids. And this has a very strong interpretation to me, which is like, to get the coefficient, I just take the conjugate of the sinusoid and integrate against it, take the inner product. And it's not obvious, right? Although they look kind of similar, they're saying quite a surprising thing. Normally, when we want to build something out of a basis, the way that we find the coefficients for the basis are, might be quite difficult. Although if we're used to orthogonal bases, perhaps not. But that's basically what's going on here. And then I tried to give you a proof for why that works last time, but I wasn't very happy with it. So because we went back into the real, we broke it up into sine and cosine terms, it's kind of easier to see if you stick in the complex terms here. So this is just math, but let me just walk you through it, because I think it's pretty straightforward. So we're trying to find the CKs, and I put a little hat on to say that it's the one that we're trying to find. Here's the Fourier analysis equation that we were given. If we change the time variable to be tau is 2 pi on t, 2 pi on big T, t, that just sort of normalizes it. So rather than having to integrate from one cycle of t, we've now got a cycle of 2 pi. Just makes the integral look a little cleaner, and we get rid of these things here. So the same thing is now it's 1 over 2 pi integral over the 2 pi cycle of x in the scaled time domain times e to the minus jkt, okay? But it's just the same thing. K is an integer. Sorry, tau is the time axis that has a one period in 2 pi. But now we substitute in for x the assumed form of our Fourier synthesis, right? So we're saying, well, we assume that x can be written as the sum over some coefficient, some terms L of CL times e to the j L tau, where that works out to be the same, this thing up here, right? And then you write it down like this. You can interchange the summation and the integral because, if you like, integration is linear. So we can take the sum over CL here, and we just get this integral of e to the j L tau times e to the minus j k tau, which we can combine to be e to the j L minus k tau. And this is the thing that we want to be 0 for L minus k not equal to 0, and 1 for L equal to k, or L minus k equal to 0. And we went through this proof showing that, well, this is actually a sinc function, and sinc function has that property. But for integer L and k, you can sort of see it just without worrying about sinc functions, which is what we're saying here is we're integrating a complex exponential, a complex sinusoid, over an entire 2 pi sequence where it completes L minus k cycles in that 2 pi sequence. That's what this form means. And L and k are integers, right? They're the term in the inside of summation and the term we're trying to get out. And if you think about it a little bit, so here I've tried to plot a sort of 3D view of, time versus real versus imaginary of one of these e to the j k taus. It's tau, so it's a continuous function, but it still has a spiral shape. And if it's an integer number of cycles, then the cosine terms are going to be, the real part is going to be symmetric, but it's going to be an exact number of cycles of the cosine. So it's going to have as much positive as negative. So that's obviously going to integrate out to 0. And then the sine part, the imaginary part, is odd. So if it's an exact number of cycles around 0, then that's even, as long as it's symmetric around 0, that's going to integrate out. So you can see that one of these spirals, if you integrate the values over the entire integer number of cycles, it comes out to 0. The only time it doesn't come out to 0 is when this term is 0, and in that case, it's the sinusoid with infinitely slow frequency, so it doesn't actually ever change from just being 1. And so this term just turns out to be 1. So the integral of over a region of 2 pi of 1 is 2 pi divided by 2 pi. You get 1 out, so you get just this thing just equals c of k, right? This is what we proved last time. I feel like this is an easier way to see it. I'm not, this is an easier way to see it as long as you're not freaked out by this idea that, e to the j pi is, e to the j theta is this complex exponential sinusoid. Okay, so that was the Fourier series, and then at the very end of the lecture I said if we let the period go to infinity, the period big T go to infinity, then basically we end up with like a signal, a periodic signal, but its period is so long that it never actually repeats in practice. So it generalizes to an aperiodic signal, and then what we're building it up out of is the sinusoids whose frequencies are 1 over the period and as many, all the harmonics. And that collapses to an infinitely dense grid of frequencies, so the entire, all possible frequencies. And we just get this. So we get the Fourier synthesis now is that rather than being a sum of e to the j 2 pi k t on big T, it's e to the j omega t, and then for each of those, for a continuous frequency value, omega in radians per second. And for every possible omega, we have some coefficient x, big X, which we're denoting as big X of j omega here. But it's a function of a single omega variable. That gives us, that's how we synthesize x of t. And then to find the x of j omegas that give us the right value for a particular x of t, we do the same thing of integrating x of t against the conjugate of the complex sinusoid and integrating it over the entire period, which is now the entire signal. So that's like, standard trick of going from a discrete value to a continuous value. So this is the continuous time for a transform. And it's a mapping between two infinite functions of a continuous variable. X of t, in general, x of t can be complex, although very often the x of t's that we're looking at have zero imaginary part. So that's in the time domain. In the frequency domain, so here's our time axis, time in seconds. Here's our frequency axis, frequency in this case in hertz, or it could be in radians per second. But it's complex, so to plot it, I'm plotting it in terms of the magnitude part and the angle, the magnitude. And here I've plotted the magnitude in dB, because that's often how we plot it, but it's just some actually non-negative value. Becomes negative when you take its log, or can become negative when you take its log. And the phase is between minus pi and pi, because it's a phase value which is ambiguous. But we have, basically, though now these look a little different. I could have plotted this thing in terms of a log magnitude and an angle. In this case, because it was a real value, the angle would be 0 when it's positive and pi when it's negative. But I could have plotted them the same. And the point I tried to end with last time is that there's nothing special about either one of these. Well, there is something special. This has got time in it. Time is how we experience the world. But from a mathematical point of view, there's no difference between these two. When you look at the equations, when you look at the symmetry between these two equations, they're just integrals against complex exponentials in both directions. It's clear that there's nothing particularly more important about the time domain or the frequency domain. Just to sort of make sure we're getting this, we can think about what happens if we want to take the Fourier transform of a sinusoid. So this is so let's assume, let's see how that works out. Let's assume that x of t is e to the j big omega 0 t. So this is a sinusoid, but it's a complex sinusoid with a frequency of omega 0 radians per second, right, which we can convert to hertz as omega radians per second divided by 2 pi to give us cycles per second. Now, the Fourier synthesis form expression is that x of t has got to be equal to the integral over all possible values of omega of x of, our function of omega here I've written it just as x of omega, just to make it clear that we're just talking about this set of coefficients. So it's the integral of x of omega times e to the j omega t. But we know that we want x of t to be e to the j omega 0 t. This is here, this omega is just the integration variable. Here, this omega is some constant. So we want this integral to basically disappear for all values of omega except omega equal to omega 0. And of course, the way we do that is by making x of omega be a Dirac delta function, right? Dirac delta function has that property that the integral of some function multiplied by the Dirac delta function gives you just the value of that function at the point where the Dirac argument becomes 0. This is a continuous time Dirac delta function, which has, in order to make this work, the Dirac delta function has to have an integral of 1, but have a infinitely small support. So it actually, it's only non-zero for one value, and at that value, it's 1 over 0. It's infinite, something like that. So it's a little bit weird to deal with, but luckily we can just think about it as a mathematical concept, and that gives us the result that we want. That when we do this integral, if we define it this way and if we define the Dirac this way, then we have the result that yes, indeed, taking the inverse Fourier transform of Fourier synthesis of this x of omega gives us this x of t. And then obviously this thing is linear, so that if we have x of t as a scaled sinusoid with some actually complex gain here, then we get the Fourier transform is just the scaled version of that Fourier transform. So we can have a delta with some weight here. This is again, but this is the intuitive idea that you have a sinusoid which is constant and which is periodic, exists, it lasts for all time, and does the same thing. It just repeats every t seconds. In the transform domain, so it's an infinite duration. In time domain, it's infinite duration. In the transform domain, it's the most compact signal you can have. It's only non-zero at one value of frequency at omega 0, and so it's this sort of that's the way that signals can end up looking very different through the transform. Okay. So there's really just one. Yeah, sorry. Yeah.
And that's the Dirac delta function.
Yeah.
It's basically an impulse at that particular frequency of the sinusoid. I mean, like at that, I mean, yeah, it's just an impulse function or something else. I mean,
Yes.
it's something more than that.
No, absolutely. It's an impulse. The Dirac is
that particular frequency.
is a basic impulse. Yeah. So that's. I mean, I was. So an impulse is an idea that was sort of very much. I don't know about for you, but for me, it's a time domain kind of idea. It's the idea of a signal that does nothing, and suddenly, has an impulse, has a hit, and then goes back to doing nothing. But here, through our idea that there's like this duality between time and frequency, this is now, I mean, if we're plotting that, we're saying that it's x of omega, x of the frequency variable, that's the delta. So now it's like, well, there's this frequency variable, and it's 0 everywhere, but it's just got this impulse at a particular frequency. And so that's the idea that the infinite duration signal in time becomes this impulse in frequency at the frequency of the sinusoid. And of course, the converse is also true, that the impulse in time becomes an infinite duration signal in frequency. An impulse consists of all possible frequencies, right? Because it's infinitely short, so it has all kinds of very high frequency content. And so that's the duality working through there as well. Okay, so basically there's a single concept of the Fourier transform, which is to take a signal, a one-dimensional signal in one domain, and express it as a sum of complex exponentials, or complex sinusoids in the transform domain. But depending on the restrictions of one domain, we get different restrictions in the other domain, and sometimes it's useful to rewrite the Fourier transform in terms of these restricted forms. And so that's why we've already seen two versions of it, the Fourier series, which we then generalized to Fourier transform. And so this is just trying to draw the contrast between these. The Fourier series, the restriction was that we were talking about a continuous signal, but it was periodic in the time domain. And what we ended up with was a Fourier transform that was a set of discrete values. It was like a countably infinite, or whatever the word is. It was like a very, very long list of discrete values, but they were discrete values. When we removed the periodicity restriction here by, the way I think about it, of letting the period get very, very long, we get a continuous and infinite x of t, which is basically an unrestricted one-dimensional continuous signal. And then these list of values get very, very close together, so they also become continuous and infinite. So this is the symmetric form where both domains are basically the same. They're both one-dimensional, continuous, unrestricted, complex functions. Now, what we're actually here to talk about is the discrete time processing. So what happens if we say, well, no, x of t is not a continuous function, it's the sampled function, which, if you like, we only define its value at a set of regularly spaced times, which we can index with an index n. What happens then is, it's a little bit strange, but what we get is we still have a continuous Fourier transform, but now it becomes periodic. And that's our x of e to the j omega. That's what we call the DTFT, which we're going to talk about now. There's a fourth restriction, which is like, okay, well, let's say now we've got the sampled signal. What about if we also make it periodic, like the original Fourier series condition? So it only exists at certain times, and it repeats every, big N samples. Then what happens is this continuous signal becomes discrete, or we can describe it by its discrete values, depending on how you think about it. And then that gives us the DFT, the discrete Fourier transform, because it's discrete in both its time and its frequency aspects. And again, we have this nice, it's also periodic, because as we'll see, it is also periodic. And again, we have a nice straight duality, where the time domain form is the same as the frequency domain form. They're both finite length or finite dimensional discrete complex sequences. They only have a certain number of unique values, which either repeat or you can imagine them just not being defined outside of a range. So these are our sort of four aspects of the Fourier transform, but they're not different. They're just different ways of kind of boiling down the math to sort of make it a little easier to work with. So, and in particular, if you really want to, you can always express this in terms of the continuous time thing. It's just that you'd be carrying around a lot of kind of, cumbersome notation. So that's why we define these things. All right, so let's talk about the discrete time Fourier transform, because that's kind of like the main event here. What happens when we're talking about the Fourier transform, but our x of n is a sequence rather than a function? And basically what happens, I mean, it turns out that all this math works if you wrote down your sequence as a set of delta functions in time occurring at the sampling intervals. Right? So if you think about x of n as just a continuous function, but a function that's 0 everywhere except for these particular values, and so we can describe it by the set of values at those times. And so if you did that, then when you took the integral, right, the Fourier transform wants to be the integral of the time domain function against this conjugate sinusoid. And then what would happen would be, well, you'd only get the values where the actual impulses occurred. And so the integral would become a summation. And so that gives us this DTFT, which we can just take as a definition. We don't have to worry about the relationship, but it's not out of nowhere. So the DTFT is defined as the sum of x of n multiplied against this conjugate complex sinusoid e to the minus j omega n, where omega is our frequency, but now we're using lowercase omega because it's in a slightly different domain. It's radians per sample rather than radians per second, right? So there's a sense of normalizing time when we go into discrete time. We normalize it to be everything in terms of the sample count, whatever that means, however we arrived at that. And so this is just sum of x of n, e to the minus j, little omega n, overall, over the entire signal, overall n. So it looks very much, it's as close as we could get to writing the continuous time Fourier transform for a discrete time signal. We write this, so this is essentially x of omega. X is a function of this normalized frequency, little omega. But we write it as x of e to the j omega for reasons that will become clear when we do the z transform. But for now, it's just a convention. So let's jump right in to try and work out the DTFT for a particular signal. And so here's our signal. Let's say x of n is alpha to the n times mu of n for magnitude alpha smaller than 1. So mu of n is the step function. That's what it means when we see that. So it's alpha to the n, which is, for alpha less than 1, it's going to be some kind of decaying exponential sequence like this, times mu of n, meaning that it's only non-zero for n, for positive n, or non-negative n. So if alpha were like, 0.6, then it would be like this, 0, 0, 0, 0.6, or 0.1, 0.6, 0.36, 0.216, etc. All right, so if you want to know the DTFT of this, here's the equation, that it's the sum of overall n of x of n e to the minus j omega n. X of n is alpha n mu of n. So we can drop the mu of n and just change the summation to be just from n equals 0 and onwards. So it's alpha n e to the minus j omega n. We can combine those two exponential terms. So it's alpha e to the minus j omega, all raised to the power of n. This is an infinite sum, but it's one that we can work out. So here's, in this green box, we've got a little identity here. If S is the sum over some range from n equals 0 to infinity of some basis c raised to the power of n, here's the trick. You say, well, if that was true, then c times S would just be like c times each of these terms, right? Which would just be raising the power of n one extra, incrementing it by 1 for each term. So it'd be the same thing, but it'd be sum of c to the n for n equal 1 to infinity. The first term, the n equals 0 term, becomes c to the 1. The n equal infinity term becomes c to the infinity plus 1, but that's no different from c to the infinity, right? So this is the same series, but just starting at 1. So if we have s minus c of s, the only difference between these two sequences is the c0 term, assuming, of course, that c to infinity disappears. So that assumes that we've got magnitude of c smaller than 1, so when we raise it to enough powers, when we think about the very end of the sequence, we don't have to worry about it. If this wasn't true, then that whole argument about c to the infinity being the same as c to the infinity plus 1 would be much more suspect. But when we've got a c such that c to the n is going to have magnitude that disappears for large n, then this is absolutely safe. And so then we just divide through by 1 minus c, and we can find that s is 1 over 1 minus c. Right? So this is kind of this neat trick, but it's an identity for a geometric series infinite sum. So here we had x of e to the j omega was this geometric series infinite sum where the basis is alpha e to the minus j omega. So therefore, x of e to the j omega is 1 over 1 minus alpha e to the minus j omega. So this is a function of omega. Omega is a continuous value. It's 1 over 1 minus this complex sinusoid. So what's actually going on here? Well, here, again, I'm trying to do the three-dimensional drawing of what's going on. This is n, the real part, the imaginary part. So 1 is here. It's like some point on the real axis. And so if it was just, if x of m were just 1, it would be this line here. But what we've got is 1 minus alpha e to the minus j omega. Well, e to the j omega or e to the minus j omega is some kind of helix like this, right? That's the complex sinusoid. So we're scaling that by alpha, and then we're negating it, and then we're adding it to 1 to get this denominator here. So this part is like this. It's a little helix scaled by alpha, where alpha is smaller than 1, remember? Right, the magnitude of alpha is smaller than 1. And then shifted so it's 1. So it's like a helix that doesn't quite touch, doesn't get as close as the actual 0 line, but just spins around this 1, 0 axis off to infinity. Now, the x of e to the j omega is actually 1 over that. So here's the actual values, right? The value of 1 minus alpha e to the minus j omega is this line here. So 1 over that is going to be the reciprocal of its length, and it's going to be a complex number whose magnitude is the reciprocal of that, and whose phase is the negative of that. So we can see that this, the length of this line is going to get, maybe somewhat close to 0, and then it's going to loop out and get to be very large. So 1 over that, when it gets close to 0, it can get pretty big. When it gets large, it's going to get pretty small. But it'll never get as small as it gets big, right? If alpha is very close to 1, we've sort of said that alpha can't be as large as 1. But if it gets close to 1, then this could get very, 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 very small here. So 1 over that can get very, very large indeed. But even if alpha was close to 1, then the other extreme would be 1 plus alpha, which would be almost 2. So the minimum would be a half. But you get a shape like this, which is just 1 over this approximately sinusoid variation, where it has these sort of close approaches where it gets large, and then these sort of, what's it called, the apogee, the point where it's furthest away, where it gets small, but it sort of doesn't change so rapidly. Because of this looping, it's periodic, right? Because of this thing is just a function of omega here. As a function of omega, this thing is periodic in 2 pi. That's the magnitude. And here's the phase. And basically, you can see this thing is kind of like it's going to go up a bit, down a bit, up a bit, down a bit. And so the negative of that will go down and then up and then down and then up. It changes rapidly at these points where it's closer to the axis, changes more slowly at the far away points when it's further away. But we have this phase. And the phase, again, is also periodic in 2 pi in omega. And so this is the DTFT, right? It's a continuous function of frequencies, the DTFT of the sequence up here. A continuous function of the frequency, normalized frequency variable omega, which is a complete description of that same sequence. I guess that's true. Yeah. But according to our understanding of Fourier transforms, we believe that we should be able to get back to that sequence from this thing. We haven't shown that yet for the discrete time, but that's the basic idea. And also what it's saying here is like, well, there's some content of different complex sinusoidal bases. There's a lot of this zero. There's of this zero term. There's rather less of these other terms, but then there's a lot of this 2 pi term, a lot of this 4 pi term, etc. So we can understand this, using our existing Fourier transform intuitions. So we were sort of thinking about that just as a function of omega. We write it as x of e to the j omega. And just so we can, just as an observation here, we noticed that when we got it, what we got was a function that was ambiguous, that was periodic in omega with a period of 2 pi. If we actually substitute, so the actual Fourier transform here, right, is it's got e to the j omega here. It's got the same e to the j omega here, right? So that's what we can do now is we can say, well, what is x of e to the j omega plus 2 pi? So what is the Fourier transform of something when we look 2 pi further in frequency? So we could just write down that same e to the j omega plus 2 pi here. We can break this exponential into 2 terms. We get our e to the j omega. We get our e to the j 2 pi n. N is the index, which is an integer. So obviously this is just some complete number of cycles of this complex phasor. So this term disappears. So this just becomes sum of x of n e to the minus j omega n, which is just e to the j omega. So we actually, just by inspection, we can see that for any x of n, x of e to the j omega has to be equal to x of e to the j omega plus 2 pi. And so that's this 2 pi periodicity that we see. And that's the big difference from the regular Fourier transform. The regular continuous Fourier transform had complex values for all frequency values, but they could be anything. Here, we've got complex values for all frequency values, but they have to be periodic. And that's actually the consequence of having a discrete sequence, having a set of function of an x, which is a function of a time variable but only exists for a set of discrete time instants. And so it's not particularly what you'd expect to be the impact, but that's how it works out. One of the nice things about making it x of e to the j omega rather than, say, x of omega is that, well, if it's x of e to the j omega, then e to the j omega is already equal to e to the j omega plus 2 pi. And so now there's no sense we have to express this periodicity. It's like it's implicit in the way that we express it as a function of e to the j omega. Which, again, will make a lot of sense when we see it in terms of the Z transform. So that's the definition of the Fourier, the forward discrete-time Fourier transform, or the discrete-time Fourier transform analysis. To go back from the DTFT to the time domain, we need an inverse DTFT or a synthesis equation. And here it is. It's basically looks quite a lot like the Fourier the inverse continuous Fourier transform. Right? This was just like the integral of our Fourier transform against the exponentials. So here it is for the DTFT. It's basically the same, but now we're only going to look at a single cycle, and we're only going to evaluate it for discrete values of n. Right? But basically, it is, in fact, the same. It's just that we only have to evaluate part of it because the periodicity means there's no point in integrating outside of this range. And the discreteness of n means that we assume, if we did it right, it would work out to be 0 for any non-integral value of n, which would work out if we did the whole thing. So we're mapping from the continuous function, continuous variable omega to this discrete value n. Also, this process of evaluating the integral of a function against a complex exponential over a single cycle is exactly what we did when we were doing the Fourier series analysis, except that had a negative e to the minus j omega, e to the minus j 2 pi k on t, something like that. But it just shows you that, because the constraints are the same, we're going from a continuous to a sequence. Because we're doing Fourier transform, we actually end up with more or less the same form. That's just a little aside. We should check that this the IDTFT looks right, but does it actually work? Well, again, we can do just substitute it in to see that it works out here. So this is the expression we had on the previous slide. X of n is 1 over 2 pi integral over minus pi to pi of x of e to the j omega times e to the j omega n integrated over omega. If we plug in our DTFT expression here, that x of e to the j omega is equal to the sum over all time indices of x of L e to the minus j omega L. Then we do the same trick of interchanging the summation and the integral here, because it's all, the integral over a sum of functions is just the sum of the integral over those individual functions. So we get sum of x of L, 1 over 2 pi integral e to the minus j, and then we've got these two exponents again, so we can fold them together. So it's the same thing we saw before, that it's this sum over an integral number of cycles of a complex sinusoid, which is going to be 0 unless this thing is 0 itself, in which case it'll be 1. So it gives us x of n, because this thing is only going to be non-zero when L equals n. And as we saw the old way, this is actually equal to sinc of pi times n minus L as it works out, but the only property of sinc we're using here is the fact that it's 0 for all integer multiples of pi except for 0. Let's just see how we can get that sinc coming out just by using traditional calculus. So this is what we had here as the thing that we were saying was equal to sinc, 1 over 2 pi integral from minus pi to pi of e to the j omega, e to the j omega n minus L d omega. So if I did my, Calc 101 procedure, well, the integral of an exponential is just you take the argument, you do 1 over that. It's the same thing. It's this, right? This for me is just total rote. This is what my calculus teacher told me, so I write it down. When it's over limits, you put the limits here, and then you express it at those limits. And so what you get here is these are the values for omega. So you get e to the pi n minus L minus e to the minus j pi n minus L. And then they're both divided by this constant value, 1 over 2 pi j n minus L. These things we can expand using Euler's equation as cosine pi n minus L plus j sine pi n minus L. And then this one is cosine cosine pi n minus L minus j sine pi n minus L. So when we subtract it, we get the cosines cancel and the j sines reinforce. So we get 2j sine pi n minus L divided by j n minus L. So now the j's cancel, the 2's cancel, and the pi goes in. This is just sine of pi n minus L divided by pi n minus L, which is what we're defining as sinc pi n minus L. Again, this is we could have gotten the same thing by rewriting this in terms of cos plus j sine. Obviously, it has to work. I actually now think it depends which calculus identity you are happier with, integrating exponentials and not worrying about the fact that the exponent is complex, or integrating sine and cosine separately. And then, this is the slide we saw before that shows us what sinc actually is, that it has this kind of this ripply thing. It's this, it's actually, it's the prototypical kind of blurring function, as we'll see later on. It's got a nice pulse in the middle, but it's got these sort of side lobes that ripple out forever. Okay, so now we've defined the DTFT. We can look at what it actually works out to be in a few cases just to get some feeling for it. So let's start off with the fundamental time domain sequence, which is our delta sequence. Something from which we can build all other sequences with only delays and scales. So if x of n is delta of n, and this is the discrete delta function, which is just 0 except at 0 where it's 1. So it's a relatively not particularly exotic. Here's our definition. X of j omega is the sum of x of n e to the minus j omega n. Well, if x of n is delta of n, then it's 0 everywhere except at n equals 0 where it's 1. So it's just e to the minus j omega n for n equals 0, which is 1. And so now we have x of e to the j omega that doesn't actually vary with omega. It's a constant value across all omega. We can write it as a little table of identities here. DTFT transform pairs. The DTFT, when x of n is delta of n, the DTFT is 1, which is the same as saying, because we've just shown that we can invert it, that when x of e to the j omega is 1, then that corresponds to x of n being delta of n. So that's the idea of this double-headed arrow, that these are a pair, a transform pair. Here's x of n plotted with our stem convention. Here's x of e to the j omega, which is a flat line. Now, before we saw that x of e to the j omega needed to be periodic in 2 pi in omega. Here we're not seeing that periodicity, but of course the constant value is also periodic with any period, because when you shift it by that amount, it stays the same. So this does obey our 2 pi periodicity, even though it's not one of the most obvious visual features of it. In general, x of e to the j omega is complex, so it's difficult to plot on a 2D plot, but in this case it's real for all values, so I just plotted it like that, and I didn't have to go off the page to plot the imaginary parts. All right, so what about if x of e to the j omega is another important basic sequence for us, a pure sinusoid, in this case a pure complex sinusoid, e to the j omega 0 n. And here, again, we can use the same argument we did in the continuous time domain, that, well, if that's true, then we want the inverse DTFT, which is this, to give us the right answer. So just by inspection, we know that x of e to the j omega must be 0 for all values of omega over this integral range, minus pi to pi, except for omega 0. And for omega 0, we actually want this whole thing just to integrate out to 1, so we'd want it to be 2 pi times delta of omega minus omega 0, so that when we integrate and then have this obligatory 1 over 2 pi, we get just the e to the j omega 0 n coming out. So this is the same answer, that the Fourier transform of this periodic sequence is just a delta in frequency, right? And now this is omega is a continuous variable, so this is a direct delta. This is the weird delta that's got infinite value over almost nowhere. Now the periodicity problem becomes more of an issue, but this is only necessary over this range of integration. So, but what that means is, well, x of the j omega has a delta in it, but it also has to be periodic, because we're talking about a periodic sequence. So actually, it can't be 0 everywhere else. This delta has to repeat every 2 pi. But that's okay. It doesn't affect here, because here we only looked at one single 2 pi range. So the full DTFT pair is that if in the time domain it's e to the j omega 0 n, then in the frequency domain it's delta of omega minus omega 0 times 2 pi, and every 2 pi shift of that. So it's a sum of those for all shifts of 2 pi k, for all values of k. Right? So it's a set of Dirac deltas, each 2 pi apart. Having solved this, we can then say, well, if omega 0 equals 0, then we've got the infinitely slowly moving sinusoid here, with x of n equal to 1 for all values of n. So just a constant n. And in that case, omega 0 is 0, so we just set this to 0, and we get this coming out. So the Fourier transform of a constant value in sequence time is a set of deltas, including delta of 0, and then every 2 pi offset of that. And so that looks like this in frequency. So here we had that a delta in time gives us a constant value in frequency. Here we have a constant value in time gives us a delta in frequency, and then its obligatory 2 pi repetitions, which again is the kind of the essential duality of the Fourier domain, that what's very spread out in one domain becomes very compact in the transform domain. Another sequence, well, we already solved this one. So the prototypical exponential sequence, or exponential decaying sequence, alpha to the m mu of n, that was the original thing we solved, that it's through this geometric series identity. It's 1 over 1 minus alpha e to the minus j omega, so that's a function of omega. Although this only, the analysis only works when alpha is smaller than 1, has magnitude smaller than 1. If alpha had a magnitude larger than 1, then this would be a sequence. It's an infinite duration sequence, right? It's non-zero for, in general, for all values of n greater than or equal to 0. But when alpha is small, when alpha is less than 1, they get very small as time goes on. With large alpha, they would continue getting larger when time goes on. And so the idea then of trying to take the summation against over all values of alpha against this sinusoid becomes ill-defined, doesn't converge, right? Because as you go further, the values of x of n get larger and larger, and so depending on where you stop, you get some arbitrary large value that you can't really work with. So we'd actually say that the DTFT for alpha greater than 1 is not defined because it doesn't converge, right? It's not something that we can ever give a sensible answer to. Mu of n, right, the step function, which is, another kind of basic function, is tricky for that reason, because that also has this property that it doesn't decay away with time, that the answer you get depends on, how long you keep on summing it up. But through some trick of mathematics, which I don't actually know, we do have an identity for this. This is the part that you'd get if you substituted in alpha equal to 1, which would by this, would give you the just mu of n alone. But it isn't this. There's also this term in here that comes out, which if you look at it is actually the DTFT of a constant value x of n equal to 1/2. I don't have a good answer as to why that works out, but that's the equation they have in the book. The equation they have in the book. It doesn't really matter, but since it exists, I give it to you there. Properties of the DTFT, well, like all Fourier transforms, it's linear, which means that if we have two sequences, g of n and h of n, and their corresponding DTFTs, g of e to j omega and h of e to j omega, if we scale them and add them together, then the Fourier transform of that is the scaled and added together Fourier transforms of the two individual pieces. Time shift, if we take a sequence and we delay it, right, we recognize this as what we do in the time domain to generate a version of g that happens n0 samples later. Well, we can simply plug that into the DTFT equation, rearrange it to try and get the DTFT of g of n coming out. And what happens is we get this constant term coming out of it, which is a complex sinusoid that's scaling g of e to j omega. And that's this kind of very intuitive thing for me as well. So I've got this time domain function. I've got, its frequency domain over here, say. And I can move it around in time. What happens is the magnitude of the frequency domain doesn't change, because the magnitude of this thing is always 1. This is just a pure phase term. But the phase changes a lot. So the magnitude stays the same, but the phase down here moves around a lot. And what actually happens in phase is it's a linear modification, that the phase is modified, right? It's multiplying by this is just adding to the phase by this amount. This is just a pure phase modification. And the phase is modified by something that's proportional to omega and proportional to the delay. And so that's where this idea of linear phase comes from, that a shift in time is a linear phase modification. It just shifts the phase down or shifts it up, depending which way you're looking. And then in my 3D spiral visualization, what that's doing is taking this function here and superimposing it on this helix. So it's like twisting it around. And the more you delay it, the more twisted it becomes. The actual magnitudes of each part stay the same, but you sort of wind it up as you, or unwind it as you shift it in time. Another thing we can do to the sequence is modulate it, right? Multiply it by a complex sinusoid in time, which is this sort of communications idea of modulating a signal onto a carrier. If again we just plug this into the DTFT equation, then this term gathers nicely with the e to the minus j omega n term, and so it just turns out that this is just g of e to the j omega for a shifted version of omega. So what happens here is that we're sort of doing the same thing. We're taking g of e to the j omega and we can move it around on the frequency axis. And what that means is like we're taking our g of n and multiplying it by different complex sinusoids, which is again just sort of stretching it onto this complex phase of this helix. So this behaves like a delay in frequency because it's the same thing. We're shifting the frequency by omega 0, and it has a analogous effect in time. The only difference being the sign of the phase modification here. This duality between time and frequency is it's very central. It's a very powerful idea because one of the things that's nice about it is that if you know something about a property of the spectrum of a signal, you can turn it around and suddenly you know something about the property of a time domain signal relating to its spectrum. But it also can get very confusing because now these terms, which are specific to a particular domain, delay is tied up with the idea of time. We can start applying them in the spectral domain, but then we get confused because well, do you mean the effect of a delay in frequency, meaning like shifting the frequency, or do you mean the frequency domain effect of a delay in time? And so you have to be a little bit careful and be aware of making sure that you know which one of those two you're talking about, because of course they're different but highly related. Any questions? Okay. Let's just do a quick example. So the point about giving you these identities is that we can now, in some cases, we can work out DTFTs without having to go back to the original equation, particularly the idea of linearity. If we have a sequence which is composed of several subsequences, and then we recognize each of those subsequences as identities, then we can just simply transform each part and then sum them up in the transform domain. So let's say we have a sequence here. X of n is delta of n plus alpha n mu of n minus 1. What is its DTFT? What is its pair here? We can rewrite this as alpha times alpha n minus 1, mu of n minus 1. And that's useful because this is just alpha to the n mu of n delayed by one sample, right, which is something that we know how to work with. So the Fourier transform of the DTFT of delta of n is just 1, right? It's the point in time going to constant value in frequency. And the Fourier transform of alpha to the n mu of n is 1 over 1 minus alpha e to the minus j omega. That's one of our identities. And then we're delaying this by one sample. So we have this e to the minus j omega times 1 times n0 here. And then we're scaling the whole thing by alpha, right? So that's what we get coming through here by applying those three identities. I didn't put that on the slide, but I hope you followed that when I was talking about it, right? So it's just, this is alpha n mu of n delayed by 1. This is alpha mu of n. This is delayed by 1, and this is the alpha coming down here. If we combine these terms, it's just we can put this on the numerator, alpha e to the minus j omega, and here's the 1 plus. If we put them on a common denominator here, then we get, excuse me, 1 minus alpha for the 1 plus 1 minus alpha e to the minus j omega plus alpha e to the minus e to the j omega over all this, these two terms are the same and cancel out. So we just get this, 1 over 1 minus alpha e to the minus j omega. It's nice and simple. But we notice that this is also just the Fourier transform of alpha to the n mu of n, the one we used in here. So it's like, wait, you're saying this sequence has the same DTFT as alpha to the n mu of n. That means it must be the same sequence, right? Because the DTFT is identical. And then we notice that, oh yeah, look, we took alpha to the n for every step, for every value of n larger than 0. And then we added in 1, which is actually the value that we sort of masked out by not including the 0 value here. Because alpha to the n mu of n for n equals 0 is just 1, which is the same as delta of n. So this is just a kind of clumsy way of writing alpha to the n mu of n. And so when we work through Fourier transform, of course, we got the same Fourier transform as we would have if we'd started with alpha to the n mu of n. But that just shows us the ways that we can use these identities to get DTFTs. A few comments about the symmetry relations, or how symmetry, the symmetries that we've looked at, work out in the DTFT domain. If we have a signal x of n and its DTFT pair x of e to the j omega, then if we have a new signal which is the time-reversed version of that, if we plug that into the DTFT equation, this thing up here, then basically we just get a change of variable. We're summing over all n. We can just substitute, m equal minus n. We get essentially the same thing, but we get a sign flip in the omega. So flipping in time is actually the same as just flipping around the omega axis. Similarly, if we take a new sequence which is the conjugate of the original sequence and then work it through, because if we take a complex sinusoid, flip it in time, we actually get the conjugate of the same thing, right? All that happens is the cosine terms stay the same, but the sine terms go in the opposite direction. So if we then conjugate it as well, we get back the original sequence. So when you plug that in, what you end up with is that the DTFT of a conjugated sequence is both flipped in frequency and conjugated. So it's a little, this sort of suggests, oh, you just do whatever you did to the time axis. Well, this is not quite that simple. If you have a real sequence, so if x of n is pure real, then it turns out that if you take the Fourier transform of the real part of a sequence, you end up with the conjugate symmetric part of the Fourier transform of the original sequence, which is to say, any real sequence has a DTFT which is conjugate symmetric, where conjugate symmetry is obtained by flipping and conjugating and taking the average of those two things. This is a conjugate symmetric sequence means that you remember that the real parts are even, but the imaginary parts are odd. So the imaginary parts for the positive frequency and negative frequencies are always the negative of each other. And what that means when you do the resynthesis is you get, x of some DTFT term for the positive frequency part, e to the plus j omega 0 n. You get the x of e to the minus j omega for the x of e to the minus j omega 0 n term, right? And they're going to have, they're going to be conjugate, and so the imaginary parts are going to be the negative of one of each other. So when we sum them together, the imaginary parts are going to cancel out. So every pair of complex sinusoids with positive and negative amplitudes are going to have the same, they're going to be scaled by the same value. And so the imaginary parts are going to cancel out, which is why we get a pure real sequence coming out here. Yeah.
Can you repeat what the conjugate symmetry implies again?
Conjugate symmetry is just that x cs of e to the j omega is equal to x conjugate cs of e to the minus j omega. That if we have a sequence that we right, so x CS of e to the j omega is equal to x conjugate CS of e to the minus j omega. So if we have our, I don't know if I want to plot it like this, but if we have our function of omega here, the real parts are going to be even, because the real part, the conjugate, is the same as itself. So it's saying that for plus omega, it's the same as minus omega. So this is the real part. And the imaginary part is going to be odd, because the conjugate of the imaginary part is going to be a negative of it. So that we have something which has got, that's conjugate symmetry, right? And then conjugate antisymmetry, where we just replace this with I and this with R, so it's the other way around, is the conjugate antisymmetric part is the DTFT of the imaginary part of the sequence. Or an imaginary sequence has to have a Fourier transform such that the real parts of every complex sinusoid cancel out, leaving only the imaginary parts. And then there's duality to that, so that if x is conjugate symmetric, that means that if x of n is conjugate symmetric, then x of e to the j omega is pure real. If x of n is conjugate antisymmetric, then x of e to the j omega is pure imaginary. And so this is because if x of e to the j omega is pure real, then we're only composing x of n out of unrotated complex sinusoids, right? So which are all intrinsically conjugate symmetric, and so the whole thing is going to be conjugate symmetric. And here we're just composing it out of sinusoids which have all been rotated by j, so they're all intrinsically conjugate antisymmetric. Of course, most of the time we're only talking about, most of the time we're dealing with x of n's that are real, and the whole complex number stuff is just sort of kind of imposed on us to try and make the math work. So let's get clear in our head what happens when x is real. Well, that means that here, right, it's this case here, that the Fourier transform is conjugate symmetric, which is just to say that x of e to the j omega is the conjugate of its negative frequency part. If x of n is pure real, then a conjugate symmetric function, which is also pure real, is just an even function, right? So if we say, well, we're starting off with x of n, but we're also assuming that it's conjugate symmetric, that's the same as saying that x is even, which means that x is equal to, x of n is equal to x of minus n. Well, from that, we know that means that the Fourier transform is also equal to itself reflected around the omega axis. So but the conjugate symmetric is the real part of the Fourier transform. So it's saying the real part is even. And if we have the conjugate antisymmetric part, then we're saying that, well, if x is real and conjugate antisymmetric, it means it's odd, which means that it's the negative part time. But the conjugate antisymmetric part is the imaginary part of the Fourier transform, and so we're saying that has to be odd. So if x of n is real, then in general the DTFT will be complex, but it has to be conjugate symmetric, which means that its real part is even, its imaginary part is odd. And so this is the picture I have in my mind of the spectrum of a real signal. A real signal, this should be omega. Sorry about that. It's just because I used the same picture from before. But if x of n is real, then its DTFT will have an even real part and an odd imaginary part because it's conjugate symmetric. And in particular, if x is real and even, then the imaginary part goes to 0. And so x of e to the j omega will be even and real. It's even because it's real, and it's real because it's even. But in this case, for symmetric real signals, both the time domain and the frequency domain are pure real and symmetric. And that just means that they're made up out of cosines. That if I have a symmetric function in time, I can compose it purely out of cosines. And that means that in the Fourier transform domain, I have to add the positive frequency and the negative frequency complex sinusoids so the sine terms cancel out, and I just get left with the cosine terms remaining. Any questions? All right, so here's, just to finish off, here's kind of a pretty important point, which is what happens with convolution through the Fourier transform. And this is like, you know, we introduced the Fourier transform because it was expressing signals in terms of sinusoids, and we've sort of seen that there were this nice property of sinusoids. Then we put a sinusoid through a linear system. It's still the same sinusoid. It's just that its amplitude and phase changes. And this is really kind of, and that's why the Fourier transform is important. But this is kind of the guts of why that matters, or why that works. So let's say that x of n is the convolution of two sequences, g of n and h of n. And let's say, well, what's the Fourier transform of this convolution, x of n? Well, here's our DTFT expression, and we've substituted in the convolution here for x of n. And now we've substituted in the actual convolution summation, right? So we don't have to use this novel symbol anymore. So the DTFT of the convolution is the sum over all n of the sum over the convolution dummy variable g of k h of n minus k times e to the minus j omega n, which is our DTFT thing we're taking an inner product against. Well, we can break this e to the j omega into two terms, and e to the minus j omega k, and then the rest, which is e to the minus j omega n minus k. And we can rearrange these, so we can actually pull out these two terms, which don't depend on n, outside of the summation over n, and then leave the summation of n in here. Right? This is kind of like, we had to know what we were trying to do here to arbitrarily break this e to the minus j omega n into these two pieces. But you can see that it's legal, that it worked. And now you can see that, well, this term, because we're summing over all values of n, we can do a change in variable, and it's just the Fourier transform, the DTFT of h, right? So if I say n dash is equal to n minus k, then it's a sum over all values of n dash of h of n dash e to the minus j omega n dash, which is just h of e to the j omega. And that sort of doesn't depend on k. And then these terms here, which is multiplying by, are visibly just the Fourier transform of g of k. And so this x of e to the j omega is just g of e to the j omega times h of e to the j omega. It's the pointwise multiplication of these two sequences, except it's not points, it's continuous values, but it's just the single multiplication at each value. You can get every value of x of e to the j omega by finding the value of g of e to the j omega for that omega, multiplying it by the value of h of e to the j omega for that omega, and we get the right value out. So we have our pair here. The DTFT of the convolution of two sequences is the product of the two spectra. And so this is this point here. Through the Fourier transform, in this case through the DTFT, convolution in the time domain becomes multiplication in the frequency domain. And that's the real payoff. Convolution is what we do with systems, what happens when we put things together in the time domain. But it's kind of awkward to deal with algebraically. If only we could treat the process of putting a signal through a system as the same as just scaling it, just putting it through a gain, then suddenly the algebra becomes very simple. Everything becomes very well behaved, very easy to deal with. Well, by looking at our signals and systems in the frequency domain, we get that. And suddenly everything is just multiplying stuff, and we can understand things very simply. Any questions about that? All right, so we'll finish that off on Monday.